I'm going to go on to our next topic, and this is a really short one, but this is a paper that I saw which talked about what would happen if a supernova went off early on in the birth of our solar system. And and the reason why we think this might actually be possible is the fact that when we look at places where stars form, including this is the Orion Nebula, about 1,500 light years away, and we see lots of stars all forming out of the same giant cloud of gas. But we also find, in addition to the tens of thousands of lower mass stars, you often find a handful of massive stars as well. So stars at least 8 times to 10 times the mass of our sun. And those stars, because they're so massive, they tend to burn out or die relatively quickly, living only a few million years. And when they die, they explode in supernova explosions. So these are extremely bright, extremely energetic explosions. And since most stars seem to be born in these very clustered environments where you have tens of thousands of stars all forming in roughly the same place, it's likely that our sun was born in one of these environments where it was also very crowded with lots of other stars and potentially crowded enough to have stars that went off in supernova explosions. And so if that occurred, would that impact the formation of the solar system in a way that we could detect today? And that's really the idea behind this paper. And what they did, this is another theoretical paper where they created a model, and in this case they had a young star with a disk of gas and dust around it, and the gas and dust would continue to feed mass to allow that star to grow, but some of that leftover material would remain to form planets. And so in this case, this was a protoplanetary disk about 200 astronomical units in diameter, or about 100 astronomical units in radius. An astronomical unit is the distance between us and the sun. And so this is actually about twice the size of our, the main part of our solar system. So if you look at how far Neptune and Pluto are, it's only about 40 to 50 astronomical units in size. But this 200 AU model does match the types of disks that we observe around other stars. And so they basically have this model, and then they have an assumption of a supernova going off less than a light year away. And there are different types of supernova. They have different, what we call light curves. And so if you look at the, there's a dashed blue line here, and there's also another one here. And this just shows how quickly the light peaks and drops off. And the numbers on this on the vertical axis is actually logarithmic. So there's actually a huge change in the intensity of the light coming from the supernova. And then the red lines show how much heating the disk suffers as a result of the supernova. And these different lines correspond to solar systems that are modeled at different distances from the supernova. And then also you might see there are different overlapping lines, and they correspond to different inclination angles. So if you have something that's completely face on, the entire disk will see the light and the impact from the supernova. But if the disk is edge on, then only the side that's facing the supernova will get the brunt of the radiation and the impact from the material. And then here is one of their models showing what the heating is like if you have a disk that's slightly inclined, but it's not totally edge on. And as you can see, most of the disk, the impact is on one side, on that right side, and the colors correspond to the temperatures. So on the far right, you have temperatures in excess of 8,000 degrees Kelvin. So the disk is definitely heated and enough to melt some of the material that's in the disk. But what's interesting is not so much the radiation, but the blast wave. So the blast wave will arrive many decades, if not hundreds of years, thousands of years later, depending on how far the supernova was. But it turns out that the blast wave will probably have the most effects. I mean, you'll have effects from the radiation, but it's the blast wave that will have the most noticeable effects. So one of them is that it can actually truncate the disk, so that material on the outer edges of the disk will actually be swept away because they're not as tightly bound by the star's gravity as the material that closer in. And so you might remember me saying that our solar system, the planets kind of end right around 50 astronomical units, and even the Kuiper Belt objects, the band of icy objects that include Sedna and Pluto, that ends right around that point as well, whereas other disks that we observe around other stars tend to be much larger. And so this might actually be one reason why our disk or our planets end at that 50 AU mark, and it could be because the disk was truncated by a supernova. One other possibility is that if the disk was slightly misaligned with the blast wave could actually churn up the material at the closest edge of where the blast wave hits, and it can actually cause some of that material to be misaligned in its orbit. And so that doesn't really explain our solar system because we don't really have planets that really far misaligned, but there are other solar systems that we've observed where some of the tilts of the planets are way off compared to the other planets in that solar system. And then finally, supernova blast waves can also deposit radioactive elements that were created in the aftermath of the supernova. So one of these is aluminum-26, and it actually, this particular model actually predicts far less aluminum-26 being deposited in our protoplanetary disk than what's actually observed in our solar system, or at least the daughter products after it's decayed. So this model is an interesting model, but it doesn't fully predict everything that has occurred in our solar system. And so whether our solar system was impacted by a supernova is still somewhat of an open question. And it turns out that even some of these other effects, like the disk truncation, they could actually be caused by other things, like, for instance, extreme UV radiation from massive stars could also evaporate disks and cause parts of the disks, or winds could cause the disk to be truncated. So there's still a lot of work to be done, but it's still an interesting paper, I think.